Okay, so we're on 3.3, increasing, decreasing functions, and the first derivative test. And we will do some examples here. So increasing, decreasing, and f prime test, the first derivative test. And now when we think of increasing, decreasing, we're thinking as we work left to right, looking at functions on there. So let's go 3.3. Let's go ahead and take a look at let's take a look at number 4. Number 4 is the graph there. And so it says, use the graph to estimate the open intervals in which the function is increasing or decreasing, then find the open intervals analytically. Okay, so when we go to look at this for the, just looking at the graph, we would look at where the y values, I mean, you can generally just look at it, but we would look at the y values that are increasing or greater than the other y values. We talked about that in terms of, I'll draw that, just a sketch graph of it. We talked about where the, to 1 and then down, talked about like where the x, like x1, x2, and then the y value, y1, and then the y value here, y2. Looking at where y2 is greater than y1 when x1 is less than x2, and that would tell you that the graph is going from left to right. The y values are increasing. And then, so when they say just use the graph to estimate the open interval where its function is increasing, the function is increasing, so from negative infinity, okay, so I'm going to say increasing from negative infinity all the way up to the value here, which is -1, right?
Mm-hmm. On x.
Yep, and so then it's not, it's the open interval, because it's right at -1, we're going to have, it's neither increasing or decreasing. So that's why it's an open interval. And then decreasing from -1 on down to positive infinity there. So decreasing on that interval. Now it says estimate, so there's our estimate. Then find the open intervals analytically. So analytically, how do we find our open intervals for where it is increasing or decreasing?
Can we just plug in numbers to see if, like, to prove f of x1 is less than f of x2?
Yep, that would be one way to guess and, well, kind of guess and check, but yeah, to show that it's increasing or decreasing. And then the other way, though, that would be the course of action that we're going to go is to do the first derivative test and look at the first derivative test, which will tell us where the, like when the, where the derivative is, well, what are our derivatives over here, just visually? Derivatives are positive or negative?
They're positive.
They're positive, and the derivatives are positive or negative?
Negative.
Negative. And so when the derivative is positive, I'm sorry, the first derivative test tells us where we have a minimum or maximum, but using the first derivative can tell us if it's increasing or decreasing, but that's not formally the first derivative test. So I gotta be, let me phrase this correctly, make sure I get it right, especially since it's on camera. So the first derivative test is a test that tells us if we have a maximum or a minimum. That's the first derivative test. Now the first derivative test does say that you go from a positive derivative to a negative derivative, you have a max. If you go from a negative to a positive, you have a min. So the first derivative test does look at positive and it does look at negative. Okay. However, like on page 177, they say the theorem 3.5 tests for increasing or decreasing. So if you want to test for increasing or decreasing, you also do the first derivative, and if the first derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. But the first derivative test would then say from here to here, you would have a max. So either way, we will do the first derivative of this. And so we drop the 2, right? And then x plus 1. And then the derivative of the inside
Is 1.
just 1. Good. So then here, we are going to be curious, right, for intervals where our critical points occur, right? Because that's going to change then. Like if you think, you know, the derivatives will change from positive to negative, so we're curious where the derivative is 0. And so we say, okay, the derivative is equal to 0, and visually you obviously can see it, but the derivative, you divide by -2, subtract 1, the derivative is equal to 0 at -1. So if you were to set up like, and you don't, if I was to put this on the test, in terms of like wanting the chart, I would put a chart on there, but you can see, you know, we talked about showing the charts that they have on there. And so what they would do is some sort of chart that's going to look like this, and you don't have to do this for your homework, but it would be a interval, and then underneath the interval we would probably, they would have a like test, they put test value, and then they put sine of the derivative. So you could either do test value, or you could just say sine of f prime, you know, and then it would be the conclusion is what they call it. Okay, so you don't have to set up the chart for this, but the interval is going to be based off of the value where the derivative is equal to 0, because on either side of 0 is a positive or a negative. And so we would say, okay, on the from negative infinity up to 1 is one interval, and then at, you know, x equals -1, they might put that as an interval, and then negative to -1, and -1 up to infinity, like that. And so then the sine of f, you would just plug in a test value, so to the left of -1, so call it -2, and you're plugging in not to the original function, that just tells you whether you have positive or negative y values. The original does, but the derivative will tell you if your derivative is positive or negative. And when you plug in like a -2, you would end up with a negative times a negative, which would be a positive. And then the derivative is 0. Then the derivative, if you plug in like 2 or 0 or whatever number in this interval for a test, plug in the number 2, you know, you're going to end up with a negative times a positive, and you plug in 2, so you'll end up with a negative. Therefore, the conclusion is the graph is increasing here. It is neither here. It is neither increasing or decreasing, then here it is decreasing, like that. So if that one was on the test, you could, I mean, either I'd put the chart here for you, so then you could just fill in the chart, or show analytically you could find this. You would want to do the first derivative, find this, and then say, and then you could just write using, you know, a test point of -2, we find the derivative is positive, therefore it is increasing on that interval, something like that. But I'd probably make a chart for you on there, and then you could just fill in for that. All right, so that's what you would do analytically on those ones, for numbers like 4 through, 3, 5, and 7 there. On the next chunk of problems, 9 through 16, it says identify the open intervals in which the function is increasing or decreasing. So the exact same thing that we just did. We could do a trig one though, since those ones sometimes can prove a little bit more challenging at times. Do you want to look at 16 together maybe? Looks a little bit bigger one, sine squared x plus sine x. So you have a sines number 16. So y equals sine squared x plus sine x. And we are wanting to find increasing, decreasing. You can definitely graph it and take a look at the graph, but what they're aiming for you to do is to do some sort of analytical approach. So we are curious where our derivative is going to have a critical point, right? And so let's go ahead and do the derivative of this. So y prime, or I guess it's f of x, so f prime of x, but y prime, same deal. So the derivative of sine squared x now sine squared x doesn't have a special derivative, does it?
I don't think so.
I don't think it does. We just do the power rule with it, right? So we bring the 2 out. So 2 sine x, and then what?
Sine is like the base.
Yep, sine's the base. So then we do the derivative of sine x. 2 comes out, so 2 sine x, and then derivative of sine x is?
Negative cosine x?
Just cosine x.
Okay.
And then plus derivative of sine x for this one is cosine x. Then here we have to set it equal to 0 to sine cosine x plus cosine x. Okay.
Can you just see where cosine x equals 0?
Well, with this, that would work. Where does cosine x equal 0? But then there's another spot, and so that's why we want to factor this. So if you take out a cosine x, you have 2 sine x plus 1. So you are curious, where does cosine x equal 0? And then where does 2 sine x plus 1 equal 0? So where does cosine x equal 0, and then 2 sine x plus 1 is equal to 0? And then, and this is on the interval. They give you an interval 0 to 2 pi, right? So x is greater than 0, less than 2 pi. So it's not equal to 0, not equal to 2 pi. So where does cosine x equal 0?
On pi over 2 and 3 pi over 2.
Pi over 2 and 3 pi over 2. Okay, and both those values fit in our interval. And then where does sine x equal a negative 1/2?
On like 11 pi over 6, and then on the other side,
Yep.
which is
1, 2, 3, 4, 5, 6, and then
7
7.
pi over 6.
So 7 pi over 6, and then 11 pi over 6.
Yes.
Okay. So with that, we picked somewhat of a doozy. So we know our intervals, if we think about the unit circle, we're looking at pi over 2, and then 7 pi over 6 out this way, right? 7 pi over 6, and then 3 pi over 2, and then out this way 11 pi over 6, like that. So our intervals are going to be from 0 to pi over 2, pi over 2 to 7 pi over 6, 7 pi over 6 to 3 pi over 2, 3 pi over 2 to 11 pi over 6, and 11 pi over 6 to 2 pi. So there's, the same thing, you could do a little chart there, interval, and then the sine of f prime, and then the conclusion from that. And so our intervals, we would go 0 to, like I stated up here, 0 to pi over 2. Now, we don't have to, like I included over here, I included at the critical point. Well, we know, if we did our math right, we know that at the critical point, the derivative should be 0. So 0 to pi over 2, so we're going to skip saying what happens at pi over 2, because we already know that. And then pi over 2 to 7 pi over 6. And then 7 pi over 6 to 3 pi over 2. And then 3 pi over 2 up to 11 pi over 6. And then 11 pi over 6 up to 2 pi. So then when we plug in these values, again, we're plugging into the derivative value, not into the original function. And so we would be just picking values between 0 and pi over 2 and plugging them in. You could think, you could use your calculator and put it in radian mode and then plug into a radian value like a pi over something, or we could try to think through what's happening for some of these. If you're looking at like whatever here, if you look at a value between 0 and pi over 2, excuse me, maybe a pi over 4, whatever, we know that at pi over 4, sine x is going to be positive, right? Cosine x is going to be positive. It's root 2 over 2, but we're not too worried at this stage what the value is. And then cosine x is going to be positive, right? So positive, 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 therefore that's going to be positive. Therefore the conclusion is that our graph is increasing or decreasing? Increasing, okay? So the graph is increasing. So then pi over 2 to 7 pi over 6, and here, you're looking at that, a good test point value probably would just be out at pi. That's an easy one. So sine of pi
is -1.
Is 0.
And cosine is -1.
Cosine is -1, so this whole thing is 0, this thing is -1, so negative, right?
Mm-hmm.
And therefore the conclusion is our graph is decreasing. And then 7 pi over 6 to 3 pi over 2, right? That one you could put a I've got to count these 1, 2, 3, 4, 5. 5 pi over 4. Now, again, we're not too worried. Well, that one, it may come into play that 5 pi over 4, maybe the values matter, but at the pi over 4s, hopefully, that one's easy because it's a 45, 45, 90. So it should always be root 2 over 2 or a negative root 2 over 2, right? So if we look at what's our cosine, what's our sine values there?
So our cosine is negative. and our
Cosine is
sine
negative and our sine is negative as well, right? So both are negative. So that's gonna give us a negative and a negative, right? So this whole thing will be
positive.
positive, and then this will be a negative.
Mm-hmm.
But this, so we do need to figure out that we would have 2 times, right, root 2 over 2 times root 2 over 2 plus a negative root 2 over 2. As I'm saying, root 2 over 2, root 2 over 2, those are both negative, so I'm just going to put negatives in there. And then plus a negative root 2 over 2. So that should yield for us,
Just root 2 over 2, right?
this one is going to end up, well, it'll be, that cancels, right, with that. And then root 2 times root 2 is 2. So, and then we'll have 2 over 2, so it ends up being 1. Plus a negative root 2 over 2. And what's a negative root 2 over 2? That's where you might need a little, you know, if you're going to think through the decimal formatting of it. You know what root 2 is? Approximately 1.41.
Seems correct.
Yeah. So then half of 1.41 is going to be less than 1.
Less than 1.
Therefore, 1 plus a negative less than 1 is going to end up being positive. Therefore, this is increasing. Then the next one is going to be we could do the same thing out here with the pi over 4, right?
Yeah.
Option. I mean, it's not pi over 4, but it's the multiples of pi over 4. So then, therefore, cosine, what's cosine going to be? Positive or negative?
Positive.
Positive. So then we're going to change that to a positive, change this to a positive, and then sine is negative. So this is a positive. This whole thing on the left is going to be negative. And therefore, this is going to be smaller than this. So that's going to be a negative, therefore it is decreasing. And then the last one, I guess we just have this little chunk between here and here. And we could probably guess that the value is going to be positive, yeah.
It's a sine graph, so it will just be maybe like the stop sign.
Like the stop sign, so. And if that's positive, then it's increasing. Okay, so that one is done, yeah. So a little bit laborious on that one, but a good trig review. Okay, your next chunk of problems, 17 through 39, on those, if you, it says find the critical numbers of f, if any. Find the open intervals in which the function is increasing or decreasing. Apply the first derivative test to identify all relative extrema and use a graphing utility to confirm your results. So critical numbers of f, essentially what we just did, right? You find where it's equal to 0, or what else about critical numbers? 0 or undefined. So that is a possibility, but this one is just equal to 0, no undefined areas. And then the second thing is, it says find the open intervals where it's increasing or decreasing, so just what we did. And then it says apply the first derivative test to determine if you have minimums or maximums, or relative extrema is what they say. So the first derivative test, we can do an example here, but I just want to talk about the first derivative test, which we referenced over here. First derivative test states if it goes from positive to negative, you're going to have a relative max. And so, okay, if it went from positive to negative, you had a relative maximum. And so, like, if you had another chart, you know, you could maybe even here say relative maximum right there, if you included that in your chart. So then here, if it's going from positive to negative, you would have a relative max at pi over 2, and then at 7 pi over 6, if it's going from negative to positive, you would have a relative minimum, maximum, minimum at the, like 11 pi over 6, 3 pi over 2. So when you look at a problem such as, maybe let's take a look at 28 there, x to the 2/3 minus 4, so, I don't think it's not going to have any. Let's actually look at 34. We could look at we could look at 28 x to the 2/3 minus 4, but it's just going to be a basic derivative. I want to look at 34 because that one's a little bit more challenging. It's not more challenging, it just raises a different issue. Because like 28, you're going to do something like this, find out where it's equal to 0, do the same thing. So let's look at 34, which is x over x minus 5. So f of x equals x over x minus 5. Okay, so f prime of x, right? We're looking for the derivative. What rule are we going to use for this one?
Quotient rule.
Quotient rule. So low
Derivative of the top is just 1.
1.
So then minus x times also 1.
Also 1, yep, derivative of the bottom, which is just 1 all over.
X minus 5 squared.
Okay, so then on the top you end up with what? Negative 5 over x minus 5 squared?
Yes.
Okay, so then we set that equal to 0, and we're looking for where the derivative is equal to 0. So we have a fraction. If we want to figure out where it's equal to 0 with a fraction, what do we look for?
Equal to 0, the top would be.
Yeah, where does the top equal 0? Because if this is 0, 0 divided by anything is 0. So is there anywhere where the top will be 0?
No.
No, because it's constant, negative 5. So, so far there's no zeros of this derivative, so that's out. But then we can also look for where, for critical points, where the undefined. And so we say, okay, a critical point where it's undefined would be at where?
If x equals 5.
So we say x equals 5. However,
Oh, go there.
in the original function, can you plug in 5?
No.
No, so x equals 5 is not in the domain, so actually there is no critical point for this one. Now, we can check the, because it does it say increasing or decreasing, I believe.
Yeah.
Find the open intervals which function is increasing or decreasing.
Yeah.
So we still will look at an interval, okay, and what is our intervals? Well, our interval is going to be anywhere where we have some sort of domain issue or critical points for increasing or decreasing. So our interval would be like negative infinity up to 5, and then from 5 up to infinity. That's where two different things or something's happening. So then we could plug in the sign of f prime, so the f prime sign, and we're going to plug into the derivative graph. So from negative infinity to 5, we can just plug in 0, let's say. And you're going to have a negative over a positive because it's going to be squared on the bottom.
Yep.
So you'll just end up with a
negative.
negative. And so what that tells us is that the graph is decreasing, right? And so then from 5 to infinity, plug in whatever, number 10, plug in 10, you know you're going to have a negative over always a positive there. So therefore this is also another negative, therefore it's also decreasing. Yeah. So we have decreasing, which means there's no sign change, which means if you go to the first derivative test on page 179, we have an example of something like that, where you have a negative to a negative for the derivative, and there's no relative extrema there. So on number 34, there's just no relative extrema, because the derivative stays as a negative, and that is what you have. So, by the way, on 32, if you take a look at 32, the x plus 3 minus 1, we don't have a derivative formula, x plus 3 minus 1. We don't have a derivative formula for the absolute value, but we know what the absolute value is doing, right?
Yep, we know it will be a v.
Making a v, where's the v going to happen?
At 2 or maybe 2. Is the plus 3 move it that way?
Plus 3 moves it to the left,
To the
right?
left,
Because if
right,
you
okay.
plug in a negative 3 here,
Oh, yeah.
negative 3 plus 3 is 0. Because our parent function, the original parent function, right, is this guy.
Yeah,
So then the negative 3
over there.
is 0, and then minus 1 drops it down to right here, right? And then it just goes up like this and up like this, right?
Yes.
So we know then a critical point, what's our critical point going to be? X equals
X will be 3. And, or negative 3.
Negative 3.
And, yeah.
So then at negative 3 we have a critical point, and so then we don't have a, like taking the derivative of this, we can't do the derivative. We don't have like a special formula for it, but we can think through what the derivative is, what the sign is. And so, you know, the interval would be negative infinity up to negative 3. The sign of the derivative,
Yeah, that's
or the sign of the graph is going to be negative, then the sign of the graph is going to be positive. And sure enough, we have a minimum value there, right? So that's on those ones. That's what those ones would look like. So, they have also, like on those piecewise functions, 37, 38, 39, 40. Excuse me. When you do the derivative of those, like if you look at 37 in that piecewise function, you can just take the individual derivatives. You don't, there's not like a specialty derivative for a piecewise function. You can just take like f of x equals 4 minus x squared, and then negative 2x. And then when you go to do the derivative, I mean, they give you the, I guess there, x is less than or equal to 0, and then x is greater than 0 for that. So when you do the derivative of this one, this is number 37, when you do the derivative of that, you can just take the derivative of this and say, okay, that's going to be negative 2x, and then this is negative 2. So you just do the derivative of this separately, and then you look at the intervals that they're on. And you don't do anything like with the derivative of the interval. That's just stay the same. So then you can just look at that and say what's happening at the where it's equal to 0. And you would look at it's equal to 0 at 0. And then look at those intervals from that. Okay. So that takes care of those ones. When you consider the functions, I'm looking at now like 41 through 48 there. It just says, consider the function on the interval 0 to 2 pi, find the open intervals, increasing, decreasing, first derivative test, using graphing utility. Those ones are just trig functions, which we did a trig function like that. So we can move past those. And then you have some problems like 51 you'll end up doing, and it says use a computer algebra system to differentiate the function. So they're looking for some sort of computer system. You can, I think you've done a few of those over the time, haven't you?
Yeah.
Although I don't know why, like on 51, why the derivative, why those ones are like specialty derivatives. T squared sine t on 51.
Yeah, that looks wrong.
Because it's just a product rule. So maybe they just want you to practice using a computer program to find the derivative, but nothing really unique there. And then you have to do some on 57, 58, 59, 60, those ones. Just sketching the derivative graph. And the f is shown, and then you have to come up with the derivative graph, thinking of like positive and negatives and what that would look like. I think we've done ones like that before.
Yeah.
So I think we're okay there. So, okay, and then more of the graphing ones, and then a couple story problem type problems. Motion along a plane on 81 and 83. So, let's take a look actually at 82, because you have to do 81 and 83. So let's take a look at 82, and then that will wrap up. So on 82 it says the function s of t, s being, remember, a distance function as opposed to like speed or something, or a position function, another way we say it. So it says the function s of t describes the motion of a particle along a line. For each function, find the velocity function of the particle at any time. And so then it states find the velocity and then identify the time intervals at which the particle is moving in a positive direction and then in a negative direction, and the particle changes directions. So on 82 here, this is S of t is equal to t squared minus 7t plus 10. Okay, so that's our position function. And so then it says find the velocity. How do I find the velocity?
It's the derivative.
Yep,
That's the slope.
yep, derivative of the position function. So to find velocity, v of t, it's equal to s prime of t. And so, because it's a slope along the position. And so we take the velocity, to find the velocity, we just do the derivative of that. So we get 2t, right? Minus 7. So that's our velocity function. And so then the question, that takes care of part A. And then for part B, you are curious where your velocity is positive, and then in which the particle is moving in a positive direction, and then identify the time in which the particle is moving in a negative direction, part C there. And when we think of velocity, we think of speed. Speed is always positive, but velocity, you can, you know, if this is my starting point and I'm moving, you know, the velocity is in a positive direction. And then when my velocity stops and then I go backwards, my velocity is a negative direction. Now my position, when I got back to my original starting point, my position was still positive, but then I go past the starting point, my position can become negative. But velocity would be described as positive until I stop, and then negative as I move backwards. So when we think about that, when the velocity hits 0, that's when you're going to change direction. So t then is equal to 7 halves, right? So at 7 halves, so what you're looking for is when is, you know, your interval, and then your v of t, which is the same thing as s prime of t, and then your conclusion on that. So your interval is going to be from 0 to 7 halves, and then from 7 halves onwards to infinity, if you will. So your from 0 to 7 halves, what is your velocity? So you plug in like 1. Our velocity will be positive or negative.
It will be negative.
Okay, velocity is negative, and then from 7 halves on, the velocity is probably going to be positive. Plug in the number 10. Ends up being positive. So the question is, where is our velocity positive? Check. Where is our velocity negative? Check. And then it says D, identify the times which the particle changes directions. When does the particle change directions?
At 7 halves.
Yeah, at 7 halves, yeah. So the velocity starts, and if you think about, again, it could be, here's my starting position, and then you hit go, and instead of moving in a positive direction, the particle moves in a negative direction for 3.5 seconds, stops, and then starts moving in a positive direction for the velocity, or the positive velocity. Okay, so that, wow, right up to 45. So that concludes 3.3, and we will work on that probably a little bit tomorrow. May talk for like 10 minutes about concavity. But